Today I will be going over Middleman problem 3.48. We're going to assume that because the wall thickness is less than 5% of the vessel radius, that we're going to be using a planar model for today's problem. So a quick rundown of what the problem statement is. A thin-walled spherical plastic container is initially filled with pure nitrogen at a temperature of 300 Kelvin and pressure of 1 atmosphere. The interior volume is 1 liter and the wall thickness of the container is H equals 2 millimeters. The wall of the container is permeable to oxygen but not to nitrogen. The contents of the container are well mixed. The container is initially stored in a pure nitrogen environment. An experiment is performed in which the container is removed from the nitrogen environment and the exterior of the container is suddenly surrounded by a large volume of pure oxygen at temperature 300 Kelvin and pressure 1 atmosphere. The concentration of oxygen inside the container is measured continuously. It reaches 500 parts per million by volume after 2.7 hours and 1,000 parts per million volume after 5 hours. What is the value of the permeability coefficient of oxygen in the plastic wall of the container? And we're going to assume here that the permeability coefficient is defined as Kp equaling beta times the diffusivity constant of oxygen in plastic over H, where beta is the concentration of oxygen over the partial pressure of oxygen. Now to start out, we're going to make our assumptions. We're going to assume that we're treating the problem as 1D, there are constant properties, no reaction. We're going to say that our A in our work is going to be oxygen. We're going to say that oxygen is dilute in the solid. B is the solid, which is plastic. We're assuming that the interior of the sphere is well mixed. We're assuming that there's constant pressure, temperature, and steady state in the plastic. Over here, we have a quick sketch of what our problem will be actually looking like. And then we further ran the sketch down into the 1D model shown here. We set up two regions. The first is inside the plastic itself, where we have the internal radius is less than r, which is less than the internal radius plus the thickness. Then our second region is going to be inside the sphere itself, where we have the pure nitrogen originally, and that is our radius is 0, which is less than r, which is less than the radius. First, we're going to be looking at the steady state section, where we have the radius is less than r, which is less than the radius plus h, and we're going to set up our first equation where we have dCA dt is equal to del Na plus Ra, and we're going to say that it's at steady state based on our first assumption. And we're also going to say that there's no Ra term because there's no reaction. Because of this, we know that the plus times Na is equal to 0, and therefore it is constant Na. Next, we're going to set up our equation for Na, where we have Na is equal to negative C times the diffusivity of A and B, dxa dr, plus xa times Na plus NB. And we're going to say that xa is equal to 0 here in this case because it is very dilute in the plastic. That leaves us with Na being equal to the negative diffusivity of A times B, dCA dr. Now we're going to put equation 1 into equation 2. Here we will say that the diffusivity of A and B over r squared times d dr r squared dCA dr is equal to 0. We're going to integrate first time and say that r squared dCA dr is equal to C1. Then we're going to integrate a second time and say that Ca equals our constant 1 over negative r plus C2. Now we're going to apply our boundary conditions. Our first one here is that R equals 0.06204 inside of the plastic, that the concentration Ca is equal to beta times the partial pressure of oxygen inside the sphere. Next, our second boundary condition is that R equals 0.0644 millimeters. Our concentration is equal to beta times the partial pressure of A outside. Plugging these in, we have beta times partial pressure inside is equal to negative C1 over 0.06204 plus C2, and beta times pressure of A outside is equal to negative C1 0.06404 plus C2. We're going to subtract equation 1 from equation 2, and that'll give us the equation here for C1 equals beta times the difference of pressure over 0.5034. Now solving for C2, we are going to plug in C1 into one of our equations here, and we're going to rewrite it in terms of C2, where we now have beta times the partial pressure of A outside over 0.031 minus 31.3 beta partial pressure of A inside. This allows us to find our constants C1 and C2, where we can now write the equation for concentration of A being equal to beta times partial pressure of A outside minus partial pressure of A inside over 0.5034 R plus beta partial pressure A outside over 0.031 minus 31.3 beta pressure of A inside. We're now going to evaluate at the radius of capital R. So our Na at R is equal to diffusivity of A times, or A inside B, dCA dR. We're again evaluating at R, and we now have diffusivity of A and B times beta of partial pressure of A outside minus partial pressure A inside over 0.5034 R squared. And this is going to be equal to our H here in the bottom, to diffusivity of AB, beta times pressure of A outside minus pressure of A inside over H, which is equal to our K, PA out minus PA in, and K was defined earlier. Inside the sphere, which is from 0 is less than R, which is less than our internal radius, we're going to set up the general mass balance here, where accumulation is equal to in minus out plus generation. However, we know that there's only oxygen coming in, there's no going out, so out term drops out, and there's also no reaction, so there's going to be no generation. Then we're going to write dN dt is equal to our Na times capital A. And we're going to rewrite our moles N as the ideal gas constant here, where we have PA in times the volume over the the ideal gas constant times the temperature. And that is equal to K PA out minus PA in, which we had determined on the previous page here, times the area right here, which is our A. Now, because the initial pressure is much less than P naught, we are going to be able to drop out the PA inside. Now, so we have D, partial pressure of A inside dt, is equal to K, partial pressure A outside. Again, we drop the partial pressure A inside from that subtractive term, times the surface area inside, times the ideal gas constant, times the temperature, now divided by the volume, which is rewritten down here. We have dPA over dt, and we've simplified this, so we now have 3 times K, partial pressure A outside, times the temperature, times the ideal gas, over R. We're now going to integrate and get the partial pressure of A inside is equal to 3 times K, partial pressure of A outside, temperature, ideal gas constant, over R, times T, plus our initial constant 1. And we're going to apply 2 boundary conditions here, which are the values of the time and what we know the parts per million of oxygen to be, which is shown over here. We can take the parts per million volume and actually convert that to a partial pressure of oxygen. From there, we can find a slope of how the system how the pressure on the inside is changing. And we do this because we've assumed that it is steady state within the plastic, how it's moving, that flux. So we can take the slope that we've calculated from these 2 points and say that 3K times partial pressure of oxygen outside, which is 1 atmosphere, times our temperature of 300 Kelvin, times our ideal gas constant of 8.2057 times 10 to the negative 5th meters cubed atmospheres per mole K, and divide that by our capital R, which is 0.06204 meters. And we can rewrite and solve this for K, which we found to be 5.073 times 10 to the negative 8 moles per meter squared, seconds, atmospheres. And that is how you solve for the permeability coefficient.